Hi, welcome to this recording concerning Unit 12. In this unit, really, it's the beginning of modern astronomy. It's more of an astrophysics because there are a lot of ideas that, it's based on physical laws. So first of all, we're going to start with, of course, Tycho Brahe observations and Kepler's laws, Galileo and his observations of actually the moon and also the moons of Jupiter to confirm Kepler's laws. Then we're going to talk about the properties of ellipse, which is the first law of Kepler, that the orbits of the planets are elliptical, and the fact that there are three laws of Kepler and how they help us basically do calculations. And then actually I mentioned that the fact that Galileo was doing his observations using a telescope. He did not invent the telescope so that we know. He actually used it, which was a toy at that time, converted to an astronomical tool. So again, Tycho Brahe was not using a telescope, so that you know, he was using observations, basically regular observations in an island in the sea, and near Sweden, basically. And he collected a lot of data. The point is that he collected a lot of data, and at that time, because of his meticulous observations, he wanted some recognition, but he also wanted somebody to help him with interpreting this data for the basically the motion of the planets and some other observations for the sun and things like that. So when Mr. Kepler basically joined him, and initially he didn't really have access to the data, or at least all of the data, but upon the passing of Tycho Brahe, he was able to access all the data, and he formulated the three laws. The first law is basically that the path of the planets is an ellipse, basically, and the ellipse is that the collection of all the points that are at the same distance from two points called the foci or the foci. Those are the focal points. So if you add this distance from this point to the pencil, and from the second focal point to the same pencil, no matter where you are on this path, it's the same number. You add the numbers the same. Some of the properties of the ellipse are: you have the major axis, which is the big axis in here. You have the minor axis. Half of the major axis, which is the value of A, is called the semi-major axis. Half of the minor axis also is called the semi-minor axis. But people by convention use the letter A for the semi-major axis, and for the semi-minor axis they typically use the letter the letter B. Okay, so you have A and B. The eccentricity or the eccentricity measures how far these two focal points are from one another, basically, and how flat the ellipse is. For example, this ellipse that you see it in here, that is highly elongated, where one of the focal points is sitting in here, the other focal points must be sitting very far. This has an eccentricity that is very, very, very close from 1, extremely high. The number E, which is this ratio, is always between 0 and 1. In a perfect circle, okay, it's 0. That means the two focal points are in this collapsed on one another, and they are only a single point. So it becomes all the ensemble of the points that are equidistant from a point, and that's a circle. Typical planets, though, they have an eccentricity that is low, usually very, very low, very close from a circular path. Exceptions, of course, are the path of Mercury, for example, and some asteroids, and some comets and things like that. They have a high eccentricity, which approaches 1 for some cases, okay? Or when you are near supermassive objects like the black hole, for example, then the stars that are near the black hole, the eccentricity is very, very high, approaching 1, okay? That's what I mean by high. It can never be more than 1, okay? So the first law of Kepler is that the planets move in an orbit that is an ellipse, and the sun sits in one of the focal points, okay? So this is the first law, okay, of Kepler. And so again, the prevailing thought in that time is that the paths were circular, including that of Tycho Brahe and including even Copernicus. But Mr. Kepler has all the data from Tycho Brahe observations and disagreed with that because he could measure the eccentricity for some of them. Actually, he started with Mars and then he continued on to show that all of them are actually eccentric. They have an eccentricity that's not exactly zero. The second law of Kepler said basically that if you can take a line and you draw it from the sun all the way to where the planet is, it doesn't matter which planet that is, okay? That's an imaginary line, so that you know it's a mathematical line. So you take a line and you draw it from where the planet is to where the sun is, and wait a certain amount of time. Let's say, for example, 2 months. The area that this line covers in that same period of time, which is in this case 2 months in this example, is the same no matter where the planet is. So in special case, for example, when the planet is far away from the sun, like for example, for the case of planets, this is called the aphelion point, which is the opposite to the perihelion point, which is very close from the sun. The area must be the same. That's basically his conclusion. When we get into physics, we will know that this has to do with something called the angular momentum. So the angular momentum is conserved. That's basically what that means. Okay. The quantity of the angular momentum is proportional to this area. So planets sweep equal areas for equal amounts of time, which means that as they are far away from the sun, they move slower to cover the same area because this radius is very big. And the area is proportional to the square of the radius and also the angle in here. So this angle must be bigger because this radius in here is shorter. So to maintain these two areas to be the same, in other words, the planets must travel faster when it's closer to the sun. So it's similar to the rubber ducky. If you experience that in the bathtub, so if you let go of the water that is close from the sink where the water is sinking moves faster than the water that is far away, and you can demonstrate that with a rubber ducky. Put a rubber ducky far away, and it's going to move slow. But when it's closer, it's going to spiral in faster. So this is similar to that. It has to do with the same thing, which is the angular momentum from physics. Okay. And this too actually has to do with the, both of them are related to the angular momentum, but this one has to do with the energy and the properties of the system in this case. So the third law of Kepler, this took him a little bit of time to arrive at. If you take the semi-major axis and you measure it in astronomical units, basically how far the Earth is from the sun, in terms of these units, the Earth is 1 astronomical unit from the sun. And the period, which is the time it takes to go whole cycle, for the Earth, it's 1 year. So you put 1 in here squared is equal to 1 in here cubed because the distance is 1 for the case of the Earth. So you have 1 equals to 1. But this is not only true for Earth, true for any of them. All of the planets also obey this law. As a matter of fact, any central object, as a matter of fact, the moon, as it goes around the Earth, the square of its distance, the cube of its distance, the average distance from the Earth to the moon, is proportional to the square of the time it takes for the moon to go around the Earth, which we know it's a lunar month, basically, okay? Lunar cycle, just slightly than a lunar month, okay? Obviously, this was kind of based on observations, and people started to doubt that, and there was a big controversy, especially related to the fact that the Earth is not the center of the solar system, and the fact that, hey, look, at that time, the prevailing belief is that things are symmetrical, and the symmetry in the skies is a circle, and in order to adhere to the idea that Earth is basically not perfect because man sinned on Earth. Again, this is the influence of some of the beliefs in religion, but heavens are perfect, so they must be circular. So there are some hidden agendas, if you wish, leading to that. So the whole work of Mr. Kepler was not completely accepted by everybody, except those who were based on observations. One of them was actually Galileo himself. Galileo basically observed the first of all, the imperfections on the surface of the moon when he directed that telescope to the moon. Okay, and then he also observed. He observed the rings of Saturn. He gave them. He thought that they were some sort of ears or something like that. So he didn't know what they were made up of. But he observed also Venus as it goes through phases when it moves around the sun. And again, because Venus is between the Earth and the sun and revolves around the sun, it goes through also phases similar to the moon phases. Okay, and he saw the sunspots on the sun. And one of his observations are actually the when he looked at Jupiter. So this is some of his observations on the moon, as I was saying in here, and the observations for Jupiter. He noted that there were 3 objects revolving around it. At times only 2. It's because sometimes the other objects they're either in front of or behind Jupiter, so you can see them. So at times you will see all 4 moons of Jupiter. So his observations were very, very helpful, because here is another thing. So you're arguing and saying that the Earth is the center of everything and everything must be revolved on it. But here is Jupiter, and it has 4 objects revolving around it. So if how come those objects are not actually revolving around the Earth? Because you can see them. Okay. For the case of Io, the closest moon to Jupiter, it takes on average less than 2 days to go around the Jupiter. So its period is very, very fast. Okay, you wait for a week and you will see it basically has gone almost 3 times around Jupiter. Okay, so these are some of these observations. Of course, they confirm Kepler's laws with all of their glory. Okay, there are more confirmations down the road when people took that same toy, the telescope, and started observing other things. Okay, so so these are the phases, as I was saying, of Venus. It goes through phases, as it is when the sun is between the Venus and the Earth. You will see like it's a full moon basically, and then it goes through phases when it's between the Earth and the sun. Okay, so again, go through crescent phases, go through all of the phases, and this were observed by him, by Kepler. Okay, Kepler, I'm sorry, by Galileo. Had it been really not revolving around the sun, but revolving around the Earth instead, then we wouldn't see all of these phases. Probably crescents, that's all. Okay, similar to the situation where the sun on the other side and the Earth is on the side. So we'll probably see it in crescent phases, that's it. But at times, Venus would be super bright. As a matter of fact, it's the brightest object, the 3rd brightest object in the sky. After the sun and the moon comes Venus. So that is a clear-cut indication that Venus is not revolving around the Earth. It's actually going around the sun. And the way to explain it is through this observation. And actually, you can go through all of the phases, to be honest with you. Okay, thank you.